Recently, there had been a claim of a massive solar storm approaching Earth that could cause a geomagnetic storm and knock out GPS satellites, mobile signals, and even electricity here on Earth. Do we have to take it seriously? Yes, as serious as the blemishes on your skin. Yes, I'm serious. We humans get dark spots and blemishes on our skin that come with hormones or aging. For the sun, surprisingly enough, has some cosmetic blemishes of its own. These are called sunspots and can occasionally get squeezed or popped by the sun, which could damage the skin of the earth. Are you getting what I mean? Well, basically the fireworks on the sun can create something called a geomagnetic storm affecting the earth. So let's understand the fireworks on the sun and how that has to do with the colorful light show in the sky. This could also be a warning sign for the GPS navigation and the communication systems here on Earth. The blemishes on the sun, the sunspots, are relatively dark, irregularly shaped regions on the surface of the sun, with a central dark region called the umbra and surrounding light dark regions called penumbra, much like the shadows during eclipses here on Earth. But, for obvious reasons, these sunspots are not the shadows cast by the objects in our solar system. Come on, how can something cast a shadow on the only light source in our solar system? Anyways, sunspot regions on the surface of the sun appear relatively darker as they have lower temperature than the surrounding hotter regions of the sun. With the diameter of the sun equaling 109 Earths put side by side, a typical sunspot has a diameter the size of the Earth and lasts anywhere from less than an hour to a few months. This helped in making some really interesting visual observations of the sun over the last few centuries. Galileo observed these sunspots in the 17th century and discovered that the sunspots near the equator take 25 days to circle the sun, while those farther north and south take longer, up to 36 days all the way near the poles. This is happening not because of the sunspots all roaming around, but due to the rotation of the sun itself. This varying rotation speed is known as differential rotation, a kind of rotation where the rotation period of the body differs from the latitude. Now, how is that possible? The sun is not a solid rigid structure. It is made of gas, that is plasma, which is charged ionized gas. As there is a constant flow of this plasma up and down till the core, this results in convection zones below the photosphere, which is basically the visible part of the sun, and the convection zones move at different speeds at different latitudes of the sun. This churning of superhot charged gases in the convection process creates something called the Dynamo effect, generating magnetic fields locally and collectively creating a huge magnetic field around the sun. It wasn't until the mid-19th century that astronomers observed something called the sunspot cycle, which is basically a regular increase and decrease in the number of spots on the sun. This is a 11-year cycle where the number of sunspots increase, reach a maximum, and then decrease. And to the surprise of astronomers, in this 11 years of solar cycle, the polarity of the sun is reversed. That means the magnetic field lines of the sun flips, turning north to south and vice versa. That's interesting, but how is all that connected to our GPS and mobile signals? Well, I'm coming there. As we know, the sun rotates differently at different latitudes. This results in a twisting and bending of magnetic field lines as they get haywire, creating something called the active regions on the sun. The magnetic fields are very strong where the active regions are located. and when hot plasma rises from the sun's interior to the surface, due to the convection, these active regions just push away the rising hot plasma. This causes such areas to become cooler and dimmer than the rest of the photosphere, which by definition is exactly what sunspots are. On one hand, the active regions with strong magnetic fields below the sunspots repel the hot plasma. On the other hand, that is above the surface, it attracts the charged particles surrounding the sunspots, channeling them along the magnetic field lines. These field lines extend out in the atmosphere of the sun called corona, creating a spectacle of fireworks on the sun. And sometimes these huge magnetic loops of plasma with high speeds break out the solar corona, ejecting out into the space called CMEs, also known as coronal mass ejections, or simply called the solar flares or storms. Now, how could this impact us here on Earth? Firstly, the ejections would have to be directly in the line of sight with the Earth to have any sort of effect on us. Secondly, our sun being an average-sized star has a pretty normal rotational speed. This means that its magnetic field doesn't get entangled as often, unlike smaller stars like red dwarfs, which are very active in this aspect. Now let's assume it's directed towards the Earth. These solar storms travel with the speed of 8 lakh kilometers per hour, taking approximately about 18 hours to reach the Earth. When solar storms reach the Earth, something strange happens. The invisible magnetic field of the Earth interacts with the incoming magnetic field, and coupled with charged particles that bend and stretch the magnetic field of the Earth, it funnels down the solar radiation towards the poles, following the magnetic lines and creating a colorful spectacle called the Aurora. Which results from the interaction of the atmospheric gases with the charged particles of solar radiation to produce light. This spectacle could last from a few minutes to maybe even a few hours. Now, this temporary disturbance of the Earth's magnetosphere caused by a solar wind or storm is called a geomagnetic storm. Well, aurorae occur so high up in the atmosphere that they don't pose any threat to people watching them from the ground. The aurora itself is not harmful to humans, but the electrically charged particles produced could have some potentially negative effects to infrastructure and technology. While on the whole, the Earth and humans and other flora and fauna are protected by our atmosphere, there are certain things that will not get any protection at all, and therefore will probably stop functioning if a strong solar flare hits the Earth. Among these things are the low Earth orbit satellites and global positioning system. Now, there are several ways in which space weather impacts GPS function. As GPS radio signals travel from the satellite to the receiver on the ground, passing through the Earth's ionosphere, the charged plasma from the sun during a geomagnetic storm enters the ionosphere, which bends the path of the GPS radio signal, similar to the way a lens bends the path of light. In absence of geomagnetic storm, GPS systems compensate for the average or quiet ionosphere using a model to calculate its effect on the accuracy of the positioning information. But when the ionosphere is disturbed by a space weather event, the models are no longer accurate and the GPS receiver cannot lock on the satellite and position information becomes inaccurate. It should also be noted that satellites up in the sky are vulnerable to strong solar flares and can stop functioning due to direct impact of plasma on onboard electronics or an additional atmospheric drag. Atmospheric drag, like friction, acts opposite to the direction of motion and tends to slow down a satellite. When the sun is quiet, satellites in low Earth orbit have to boost their orbits about 4 times per year to make up for the atmospheric drag. When solar activity is at its greatest over the 11-year cycle, satellites may have to be maneuvered every 2 to 3 weeks to maintain their orbit. For example, during the March 1989 solar storm event, NASA's Solar Maximum mission spacecraft was reported to have dropped as if it hit an invisible brick wall due to the increased atmospheric drag. At most, the lightest and most common of these storms could cause a minor radio disruption for a brief period. These events never directly harm life on Earth, as most of the harmful radiation is deflected by Earth's own magnetic field. However, let's just assume that everything was to perfectly go wrong. What would it be like? The last time such a big event occurred was in the year 1859, when telegraph systems all over Europe and North America failed. Widespread blackouts and electrical disruptions occurred due to the induced current in the grid and transformers that burned all the parts of hardware as current and voltages in the windings became abnormally large, leading to heating effects. Back then, we didn't have much technology that could disrupt the global network, but what could happen if this storm hits today? The world is so dependent on technology. Luckily, we had missed such an event in 2012 when Earth was ahead of the solar storm by 9 days in its orbit. Had we been unlucky, it would have caused widespread power blackouts and basically disabling everything that plugs into a wall socket. Most people wouldn't even be able to flush their toilet because urban water supplies largely rely on electric pumps. Adding to the worsts, GPS navigation could go haywire, disrupting many activities depending on it. According to a study by the National Academy of Sciences, the total economic impact today could exceed $2 trillion, or 20 times greater than the cost of the Hurricane Katrina. Multi-ton transformers and grid lines damaged by such a storm might take years to repair and restore. However, it should be realized that the magnitude of the solar storm has to be very big to have this kind of impact. The one in July 2021 was not of that kind. Thankfully, today the Space Weather Prediction Center, with the help of satellites like SOHO, could easily issue a warning alert if anything of such a scale were to occur. And we would have a minimum of 17 hours to take an action in advance by shutting down satellites, power grids, and other such precautions when the danger is at its highest, thereby ensuring that the outage is as brief as possible. Now we are into the new solar cycle that started in early 2020. So we would expect to see a peak in solar activity during 2024 to 2026 and gradually dip to a minimum in the beginning of the next decade. While the solar activity and sunspots are serious stuff to study for scientists, but for amateurs and space enthusiasts, it's a recreational activity where they go out to observe sunspots using telescopes, taking utmost precautions while doing so, like using safe solar glasses, solar filters, and age-old projection methods to observe the spots and fireworks on the sun. So take a deep breath, relax. The sun has been doing a lot of good to us and to the earth constantly for eons. Where humans are constantly doing bad to the earth. Think of it. As always, thanks for giving us space and time.